Hey, good morning, welcome. Let's see, we are going to start a big chapter here today, so I want to get jumped in and get started right away. And I'll probably even do a couple little, I don't want to say shortcuts, but I'll call that focusing on the priorities. How's that? And leave some things for the author to discuss here. And so we are going to shift gears a little bit. We're going to head into magnetism. This is the last chapter before our first exam. And so now we have done 18, 19, 20. Yesterday we did 21, and now we're going to do 22. And so this is, like I said, is a big one. It's a long one, but I guess I'd say it's both easy and hard. It's probably hard because it's new stuff. Magnetism is always hard, but what is easy is it's very visual. And so I'm going to take advantage of the book. The book's got some really good chapters, and you really have to visualize this in 3 dimensions. And so that's kind of my starting point in saying, all right, let's make sure we look closely at the book. So I'm going to reference the book quite a bit and say, okay, look at that. So maybe as you're watching this video lecture, you might want to pull out the book and say, okay, there's that picture, there's that picture. I kind of see that and see where he's kind of heading with that. So that would be my recommendation, is to have these pictures in front of you. Now, with that said here, let me just put here on the board, all right, chapter 22. Our first step into magnetism. And of course, depending on your background, all of this may be new. This first section, I'll call it 22.1, is kind of the terminology, kind of the idea of what are magnets. And so maybe the best way for me to begin is to come over here to this table, maybe move most of my equipment over here to my right, and then focus on this one all by itself. This you might call a compass. What it is just a piece of iron, and it has a lot of, I guess, history behind it. Let me not take the time to go into the history, but if you notice when I bump it and let it go, as it shakes and it moves along, it naturally wants to point what I'll call near north. It's not exactly north, but it's near north. And so some of the earliest discoveries, I think it was Marco Polo who discovered this, and when he went over to China and found that, you know, this was kind of a kid's toy, but he realized it was a great navigational tool that pointed towards the north. And in our case, we spray painted the end red. And so we can keep track of which one points north, which, by the way, would mean the other end points south. And so our first step here is to say that when we're dealing with magnets, we are going to have 2 sides to them, 2 poles to them. We are going to call one side a north pole and the other side a south pole. Maybe a better word is north-seeking pole, because a lot of times when we talk about magnets, we also talk about the geography of the Earth. And so when I come over here and I look at this compass and I say this red right here is the North Pole, I do not mean this is where Santa Claus lives, okay? Santa Claus lives in the geographical North Pole, if you still believe in Santa Claus. Okay, but the polar bears are in the geographical North Pole, right? And the penguins are in the geographical South Pole. But when I call these north and south poles, I do not mean a location in the sense on the Earth. I mean it's a location on a magnet. It's a one side versus the other. That means if I held it in my hand and let it freely spin, it would settle in, so one side seeks north and one side seeks south. So we'll label them N and S and then call them north poles for short, but we mean north-seeking poles. Okay. Now, Watch this for a moment. Let me get rid of this one again. Here's a good experiment of you might take a magnet. And so here's a magnet. One side's going to be north, one side's going to be south. Not sure which one is which. I'll just put it in what I'll call a boat. Maybe I'll start by roughly lining it east and west and just add some water until it floats, and so now it can freely move. And I guess there's going to be a little bit of water current as I pour it in. But if I let it settle, then I won't take as much time for it to completely settle down. But you can see one side ended up pointing towards the north. And so I'm going to put a little black mark on it so we can keep track of it here in the lab. So there is the north-seeking pole, and the other side is the south-seeking pole. Now, I say that because if I come over here and do the same thing with another magnet, all right, I'll put it in my little boat. Maybe I'll put the boat kind of east and west and let it go. Okay. And clearly, then this side wants to go towards the north. All right, so I'll put a little mark on here so we can keep track of that here today. All right, so I know which one's north and I know which one's south. And let's ask then how two magnets might interact. What would happen if I brought this magnet near that magnet? So maybe I'll bring this south pole near it and see what happens. So hopefully the first thing I get is there is an attraction. Okay, there is an interaction. Now in this case, it looked like the north from the one in the water is attracting to this south. And what if I turn it around? Whoa. So it looks like the north pushed away the north and then got attracted to the south. Maybe I'll turn it around again, so I'll go south. Oh, it looked like it pushed away the south and attracted the north. Well, I think you're seeing a pattern, because one thing nice about magnetism is the features of magnetism match the features of electronics. And so we had things like charges repelled when we did our electricity a couple of chapters ago. We're seeing the same thing. We're seeing these like poles repel each other here. And so I'm going to say then that if I take a second magnet, and maybe I'll draw two sets of pictures here. But the lesson hopefully observed here is that, number one, magnets do interact, right? We have names for each side of the magnet, a north pole and a south pole. Again, north-seeking pole, south-seeking pole. And we see that they interact, and so something like this, when we bring the like poles together, they're going to repel each other. And so like poles repel. And we saw that for electricity. We saw like charges repel. And then, of course, unlike poles attract. And so this is our conceptual start here. We're learning our vocabulary. We're learning the words of them. In fact, your author does a good job with this in his first couple of pictures. In fact, he does the Northern Lights right here, the Aurora Borealis, and we'll come back to that picture. But in this very first section, he has a pile of magnets here, and he labels north poles and south poles on them. He does this little picture that he says, okay, if you hold a magnet or a compass, one side of it, and so here's the one on the string, will seek towards the north. Okay, and so he'll call that a north-seeking pole. And that's what we saw here. Here's something, though, that probably should be emphasized. Remember we said the opposite poles attract? In fact, I'll come back to this picture, but his second picture is exactly what I just drew here on the board, that something like this would repel because like poles are near each other, and here, unlike are near each other, so they would attract. He even does something more than what I can do, and something that is a little different for magnetism that wasn't the same for electricity. And so this will be a chance for me to say the same thing again, that one thing nice about magnetism is it has a lot of the same features of electricity. So the stuff we already learned, we kind of just follow suit. Now that's good and bad, because there is not every feature the same. And because it's not every feature the same, it's easy to confuse those. It's also easy to confuse them thinking, oh, this is just the same thing, and you use what I would call the inappropriate word. So instead of saying North Pole, you say the charge of north or something. No, it's not charged. Our electronics has charge. Our magnets have poles. Okay? And so be really careful with the terminology. But this visual picture is really nice because your author then is trying to point out there is something quite amazing and very different, and you'll understand this a little better before the chapter is over, but you cannot make a single pole. You cannot make what we call a monopole. See, for electronics, we could make just a negative charge by itself. We say, here's an electron, we have just a negative charge. Or here's a proton, we have just a positive charge. If we had them close together, a positive and a negative, we ended up with a dipole. When it comes to magnetism, we always have dipoles. There never is a monopole. And so here's kind of his mental experiment. He says, what would happen if you took one of these bar magnets and actually broke it in half? And so maybe I, take this magnet and I go back to our shop and I run it through the bandsaw and I cut it into two pieces. Well, what do I get? Well, if you break this magnet apart in an attempt to take and separate the two poles and have what you might call a monopole, so I have just a north and just a south, turns out, and you'll see this on a more of a microscopic level, that you really end up with two magnets. You break this apart, and then this becomes the south pole and this becomes the north pole. And as you'll see, it's because inside here is really microscopic billions of little magnets connected together, and all you do is have either more of a billion or less than a billion, and so when you separate them, you always get a north pole and a south pole. And in fact, there is no actual piece of material that makes the pole like an electron or a proton. And so that's what this picture is trying to say, starting with one big magnet, making now two magnets, now making four magnets, and so forth and so on. So sadly, the field then, if you remember the field from a dipole was more complex than a single monopole, the same thing is going to be said here. So again, that's probably what makes magnetism a little bit harder to digest. Now, let me come back to this first picture I was saying here, is because this can be a confusing topic for students, because let's go back to the name. Why do we call it a north-seeking pole or a north pole? That's because it seeks towards the north. But also remember, opposite magnets attract. And so in this visual picture, your author is trying to say, and we'll again get more detail, but the core of the Earth creates its own magnetism. Has to do with the spin of the Earth and the molten lava and material. So more on that in just a second. But he's trying to say we can visualize the Earth having another bar magnet in. See, the one in our hand, the compass, then interacts with the one in the Earth. But remember, opposites attract. Opposite poles attract. So if the one in your hand is a north pole, seeking north, wouldn't it be attracted to a south pole? So look carefully at this picture. Did you notice the author put, for the magnet that's in the earth, right here, there is a magnetic south pole at the geographical north pole. So it's worth repeating. What pole is at the geographical north pole? What magnetic pole is at the geographical north pole? It's a magnetic south pole. Now when you say that by itself, it sounds silly. Why don't we call the one at the north pole the north pole? Well, that's because we wanted to call the one in your hand the north pole. The one in your hand is seeking the north. And so you could argue whether or not this is a very good definition. I totally get that, but because opposite poles attract, that is our definition. And that's what this first section is. So again, the one in your hand, the one that seeks north, is called a north pole. Since opposite attract, the one in the earth, the magnetic pole in the earth at the geographical north pole is a magnetic south pole. Okay. And so that's why you have that. Now, notice also that your author has tilted it a little bit. Notice that the magnetic south pole is not directly at the top of the earth where it spins. That's why earlier on I said, and I'll pull this kind of away here and bring my compass back and say that's why when I have something like this, I will say that is a north-seeking pole, and it points kind of to the north, not exactly to the north. Because again, based on the spinning of the earth, and it changes over time, then where it actually points is not truly the North Pole. And so we're close. Actually, in our area, it's off quite a bit. Part because of our angle of where we are, part because of the angle in the magnet, but another big part is the magnetic effect of these mountains that are near us. And so it would be like me coming over here and saying, aha, putting another magnet near it, and the effect of this other magnet then means this points off of true north by quite a bit. And so that's what kind of happens in our area. All right, so if that makes sense, let's move into section 2, where your author says, okay, then these are the words. Where does all this magnetism come from? And his, I think, best picture to kind of illustrate that, and for me to kind of demonstrate that, is to say magnetism actually comes from moving electrical charges. This is what's going to make magnetism kind of hard, because to make charges move, we need our electricity. So we studied all that, and so we've got to have a little bit of electricity around in order then to have our charges, which are moving, and then that makes the magnetism. And so we often have both effects at the same time. Now, we'll try to do our best to separate those and keep those a minimal effect as possible, especially this first chapter. But that's going to change significantly in the next couple of chapters, where we have an interplay between them almost on a constant basis. And so one of my goals here today will be try to point out which is what electrical effects that we've already studied and which is magnetic effects. All right, so you can also see, I hope, why we did the last 2 chapters about Ohm's law and current, and realizing that current is the flowing of charge. Because even though I didn't say it during the last 2 chapters, we were actually creating magnetism every time we hooked up our circuit. Every time we hooked up our circuit, we made current, and that current is a moving charge, and that's what this second section here in the book is about. Where do we get magnetism. And so we like to say this, and I'll call this section 22.2. I'll even kind of separate it into two pieces. We'll call these ferromagnets and electromagnets. But the words I was just using is that electrical current is the cause or the source of all magnetism. And so, in other words, there's not another little particle like the electron and the proton were the cause of the electric fields, but when those things move, they make our magnetism. Maybe the easiest way for me to demonstrate it is with some of this circuits up here. I have a box of nails. Now, if I were to take maybe I better do some paper clips too. So here's some paper clips. But I want to show you that by itself, this piece of metal is not a magnet. This wire is wrapped in a circle, let me call it a coil or a solenoid, is not a magnet. I can't pick anything up. Now, if I come over here and grab a magnet, then sure enough, that is a magnet. And let me put it off to the side here. But if I were to do this, and so I've got my power supply here. Let me hook it up to my solenoid. Let me turn it on. And I don't know if you saw it, I actually picked up one paper clip. Now that's a lot of current for this little thing, so let me turn it off, give it a chance to cool down. But I actually could pick this up. Watch. But if I turn it off, it falls away. This is my little proof saying, look, what makes the magnetism is when I have the current. And current is this moving charges. This is the point I'm trying to make. Where does magnetism come from? All magnetism comes from these moving charges. Now, this by itself doesn't make a whole lot of magnetism. I don't even know if I can pick up one nail. Maybe if I smother it, it'll pick it up. Let's see. Oh, yeah, I can. All right. So turn it off. And so it drops off. And so again, just trying to show you, where does this magnetism come from? Moving charges. Let me show you kind of a fun historical one here. Here's Oysters Experiment. This was actually has a fun little history because it was during a lecture that Oyster was given where he actually noticed this effect. The point of the lecture was to emphasize how electricity and magnetism were two different phenomenons. And they have a lot of the same properties, but they weren't the same. And the whole thing was not to confuse them. And then he puts this wire near this magnet or compass. So let me pull this off so you can see this a little better. This is just like that compass over there. It's got a red side which points towards the north. We like to, for whatever reason, paint it red, the one that goes towards the north. For the overhead, we drilled a little hole in there because once I put it on the overhead here, you can't tell which one is red. But this red one here is the one that's pointing north, or kind of north, because this has a lot of magnets in it. So it's actually pointing kind of in this direction, and then by the time it gets on the overhead, it flips it that way. So not worrying about which way it is right now. I just want you to see that if I take this wire and a big car battery and a switch. And so when I tap this, there will be hundreds of amps flowing through here. And so I won't tap it for very long. See, even that short time, the wire already feels kind of warm. But just to show you, I'm going to lay the wire near it and tap the switch on the count of 3. 1, 2, 3. Whoa. I'll take my finger off. I'll do it again. 1, 2, 3. Whoa. And it's already feeling warm. So I'll give that a chance to cool down. But again, my point here is to kind of set this up. Where does magnetism come from? Moving charges. And so we know that there is some kind of pattern, some kind of interaction between these charges, which when they move, we now have magnetism. So I want to emphasize that. We don't have magnetism until they actually move. And so an electron by itself makes an electric field, and an electric field only. But an electron that is moving makes both an electric field and a magnetic field. And I'll say it again, that can be kind of the hard part of this, is recognizing that both are going on at the same time. Now, what I just showed you falls into this category right here, an electromagnet. And what we mean by an electromagnet is the current is then created by this power supply. I used this power supply for the solenoid. I used this power supply for the wire. You clearly know from the past chapters about Ohm's law, voltage and current and resistance, and you're going, okay, well, I see that when the current is on, there's magnetism, and when the current is off, there's not magnetism, and hence the name electromagnetism. So we call that electromagnetism. In fact, it gives me kind of a fun chance then to maybe dive a little deeper, because what would happen if I did this metal bar inside here? Now, let me show you again without the metal bar inside. So I'm going to turn it on, and I'm going to try to pick up a couple of nails. Nothing real exciting. Let me put a core in here. Happens to be a piece of iron, but I should emphasize again, notice it doesn't pick up any nails by itself right now. But what if I put the core inside the coil and turned it on? And so, again, I would still call this electromagnetism, but could you tell it was a lot stronger than it was just by itself? And so let me emphasize, where does all magnetism come from? All magnetism comes from these moving charges. And here's what your author is trying to show you here. Remember that the iron bar also has a bunch of electrons in it. And they are not stationary, they are moving. And so when I say all magnetism comes from moving charges, I don't mean they have to be moving charges from my power supply. They can be moving charges just from nature itself, because the atoms are going around. I would describe it this way. Let me kind of take this bar magnet, or it's not iron. Let me kind of draw a picture here and say, okay, here's the end of it. Let me try to draw it kind of three-dimensional here. So here it is going backwards. Why don't I just try to draw two atoms? I won't try to draw too many. I think it'll make the picture kind of complex. Why don't I put a nucleus here and a nucleus here, okay? And this happens to be iron for reasons we're not quite ready to get into, but iron has a very, very strong magnetic effect. It's not the strongest, but it is one of the strongest, and it's a cheap, strong one, so we use iron a lot. And what would happen is the electrons, so maybe if I let the electrons be orbiting around in blue, and if they're just left to their own, it would be what I would call an equal randomness. That is, if I were to look at one atom, maybe it's going clockwise, and if I were to look at the next atom, maybe it's going counterclockwise. And in fact, if I look at another atom, maybe it's orbiting around a whole different plane clockwise, and this one, a whole different plane counterclockwise. My point is, a random piece of metal without any other effect is not going to have a net motion. All of them, these electrons, are going to be orbiting, and there's probably an equal number going clockwise and counterclockwise. And because of that, you might say their magnetism is individually, but collectively as a whole, they fall apart. There's no net motion to it. They're not synchronized. Maybe kind of a weird example, if you were at a busy airport or train station and you're standing up on the balcony looking out, you have people going left and right and forward and back, and people going up the escalator and people going down the escalator. And the net effect is no net gain. There was 1,000 people on the ground floor, and a moment later there's still 1,000 people on the ground floor, right? There's just no net effect. And that's what I'm trying to say is happening here. But what if I were to get all of those electrons orbiting in the same direction? If I were to get them to be synchronized. And so this picture here changes to this. Counterclockwise. The next one. Counterclockwise, the next one. Counterclockwise, the next one. Counterclockwise, right? So instead of having these random people at this airport, let's say this is a show, and there's a giant band in the airport. And the band then all marches to the same beat and moves across. Right, then there's a net effect. They're all synchronized. And so this is how I can make something magnetic without the effect of a power supply. Now, this material is what we call soft iron. Now, it's soft in the sense that if I took a machine, I couldn't bend it, but it bends pretty easy. In other words, here's what happens. Is these electrons are going in a random direction if I encouraged them, if I forced them to be synchronized. And it doesn't take much effort, but that's what's going on here. This makes a small magnetic field once I turn it on. That small magnetic field then encourages these to be all in the same direction. And then once all of these are in the same direction, and I should be careful, it's not all of them, it's not even the majority of them. It would be super, super strong if we can get that. But just if I get a high percentage of them going in the same direction, then this is the main cause of the magnetism. And so that's why, if you turn this on, this is actually a magnet. As you saw, I can hold one nail. But it's the small effects of this one that encourages these to line up. And the real strength of the magnet then is from the alignment of the electrons in here. And so sure enough, I now have a very strong magnet. And what's nice about the soft iron is once I turn it off, this is at room temperature, which means what? It means the atoms are banging into each other a little bit. And they'll unalign themselves once I turn that off. So this has enough strength to make them align, and as long as that is on, these are aligned. As soon as I turn that power supply off, then these bump into each other and they misalign. They're not aligned anymore. And so it goes away. And so that's the nice thing about this electromagnet with this iron core. And in fact, your author has, I think, a pretty good picture of what this might look like if you could take a slice of this metal on a microscopic level. So you take this little piece of metal, maybe you slice a piece in the middle real thin, and what you would say is maybe a dozen atoms will line up with each other and kind of make a north-south. But then another dozen will line up in a different direction, and another dozen a different direction, and another dozen a different direction. And what you have is randomness. And that's what I have right now. I have this randomness. And this will not operate and pick up. They're not working collectively. What I need to do is to get them to line up. And so this is kind of the step in that direction where they sort of line up. This one doesn't even behave closely. This one is kind of lined up. The other ones are lined up. And the net effect is a magnet. It's a current, but it's not hooked to a power supply. Okay? Now, don't get me wrong, this is where it can get kind of confusing, and I still, I guess, would call this an electromagnet because I still need the original current to encourage these to line up. But maybe that will help you understand then this. How does this always remain a magnet? What we're going to call here a permanent magnet. Or in this case, since it's made out of iron, we'll call it a ferromagnet. What's happening in this one? And I would say in this one, it's really the same thing that I just discussed, but here's something very important and different. This iron is a little different makeup, and it is very strong iron. In other words, if you line them up, they don't fall apart because they bump into each other, at least at this temperature. Now, if I were to warm this up very, very, very warm, it would behave like this one. And they would bump in hard enough and misalign. So I would say both of these are kind of doing the same thing. It's just this is not warm enough to break apart at room temperature. And so that's why I have both of these. This is one that I can control turning on and turning off. This is one I could not control turning on and off unless it was much warmer in here, maybe a couple hundred degrees Celsius. But the way it is right now, it's just going to stay permanent. And in case you're curious, how did it ever get that way to begin with? Well, it was once molten. And so what we did is we made a tray and we poured the molten iron in there. And underneath it, we had this coil. Or we put it inside and we let it cool while it was in there. And so everything was aligned, then it cooled down because when it was a liquid, it could easily move around. Once it cooled down and became a solid, it's now locked into place and it's going to stay there until they bump enough. And so one of the worst things for a magnet is that. I just misaligned a few billion of them. Fortunately, that's not that bad. I'll misalign another billion. Now, I would have to do this a long time to make that not be a magnet. So let me try it with something a little smaller, a little weaker to try to illustrate this. Here I have a nail, and the nail is made out of iron. That's good, but there was never an attempt when they were making this nail to make it a magnet. They were just trying to make it out of iron to make it strong. And so I have a paper clip right here. And so if I show you, this is not a magnet. See, a real magnet would pick this up. Here's a real magnet, easily picks up the paper clip. Okay, but this, no way. Now, can I get these to align? Well, maybe I can get a few of them to align. Right here, I have a magnet, a really strong magnet. Maybe I shouldn't put it too close to this. But I'm going to take this nail and I'm going to align the nail with the magnet. So right now, this magnet, permanent magnet, ferromagnetic, is trying to twist all of these to make sure they're all going in the same direction. Now, it's having a hard time because this iron nail is really strong, but I'll help it out. I'll slap it a few times. And every time I give it a shock, a few billion twist. And they twist in alignment, not out of alignment like when I was throwing it on the ground. They twist, excuse me, into alignment. And if I get maybe about 10 billion to line up, so did I do it 10 times? I can pick this up. Oh, it wanted to. Oh, 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 bummer. Might have messed it up a little bit. Yay. Not quite enough to lift its weight. But close enough. Hopefully you can see it's magnetic. And of course, a few thousand times of that, and we're not going to have a magnet anymore. It's why I always kind of interesting when you see some of those advertising commercials that will sell you a magnetic hammer. And I go, sure, for the first 3 months it's magnetic. How long are you going to use a hammer for? As you beat it along, it probably won't be magnetic for very long. But it's also why those magnetic screwdrivers are really nice, because they can hold the screw, but if you start using them to pry and push and don't use them correctly, they demagnetize. And so the magnetism plays into a role here. And I brought this one out here, again, just to illustrate kind of the same thing. It's harder to see, but it does a better job of illustrating how incredibly strong this can be. Because this has just 2 batteries, 2 1.5 volt batteries. This is 3 volts of batteries. Now, what's sad about this one is you can't see all the coils this makes, but you can begin to see the wires that come off, and they wrap around behind this black plastic here 10,000 times. And there's the iron core. And so when I turn the switch on, that makes just a small amount of current. That's not where the real strength comes from. That's just the current trying to get these to align. Then the real strength is all these electrons aligned in here. I'll turn it off because the other half of this is right here. So if I put this together, I want to convince you they don't stick. This is not a magnet yet. But if I align it and turn it on, it does stick. And it is incredibly strong. There's no way I can pull this apart. It is just incredibly strong. And of course, once I turn it off, the temperature in the room bangs those together, misaligns them, and now our magnetism is gone. And so there is this section 2 of the book where the author is trying to say, hey, where does this magnetism come from? In fact, he goes a little bit deeper in this and says, okay, so if our magnets are now interacting, so maybe I'll say here's a north and here's a south, and here's another magnet, and I'll just make them attract each other, so I'll put the south near the north. You might remember this same discussion that we had in, I guess it was chapter 18, where we said, now, if there's a force of attraction between them, how does it happen? What is the mechanism? How does this create a force on the second one? And do you remember that thing called an electric field? Remember we said, what was the point of the electric field? What really happened is the first one made a field, and then it was the field that interacted with the second one. It wasn't just that there were two charges, it was that there was a field effect. Well, the same thing happens here with magnetism. There is a field effect. And so I'm going to then represent that this first magnet makes a field. And let me not put any arrowheads on here yet. And maybe my drawing isn't as well as I would like it to be. But if those blue lines are representing this field, I'm hoping it looks like the dipole field we saw for the electric field. That is, the dipole that I have here, this is a magnetic field. Now, again, don't confuse a magnetic field with an electric field. But we get that same shape, right? They would start at some pole and terminate at the other pole. Now, again, I don't know if this is helpful or more confusing. Remember, electric fields, we said we made the definition of an electric field because we couldn't see with our eyes. But let me hold it the same way. Here's the North Pole. I'm trying to say that around this thing is a field. And I can't see it with my eyes. But what we'll do is we'll draw pictures. And we'll say, okay, what is the magnetic field? And our definition of the magnetic field will be the direction that a compass would point. All right. So here's my compass. And let me remind you, the red one is the one that points north. It's a north-seeking pole. So if I were to hold this up and put it right here, do you see how that compass then would be pointing towards the South Pole and away from the North Pole? I could move this compass to here. That would be the field. 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 And I can move this all around. It might be easier to see on the overhead if I turn this light back on. Put the bar magnet on here. Now, of course, once I do that, you're not going to be able to tell which one's the north, but I'm going to put my finger on the black dot, so right there. So this is the north, this is the south. If I put my compass on here, right here, see how it is pointing towards the South Pole, 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 away from the North 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 Pole. Maybe you can see it better when I have something that's got a whole array of magnets. And so I'll put this on here. sadly, some of them are a little confused. And so I'm not the most excited about this one. But it should be pointing away. And so most of these are pointing away. And that one should be pointing, away, towards. I guess, yeah, towards. So this is pointing towards, sorry, I got myself confused between here and there. So towards, and so it's pointing towards the South Pole. Here's what I'm trying to get you to visualize then, because again, we have no way to see it with our eyes, but we have surrounding this magnet something called a magnetic field. And it's the magnetic field that then interacts with that second magnet. And so we're going to draw our fields. I'll pick on blue, but the big thing is the arrowhead points in the direction a compass would point, which means it would point away from the North Pole on that magnet and would point towards a South Pole on the magnet. And that hopefully is what you see in that big array. You might actually be able to see it with this old array and this strong magnet. If I just put it here and I just kind of move around, you can kind of see the outline, and there's a few of them that are off, but most of them follow the nice pattern of what does the magnetic field look like. And again, sadly, it's kind of complex, but it's not something we haven't seen before. It is a dipole. Of course, this is a magnetic field, not to be confused with an electric field. It probably then is worth going back then to that picture of the Earth here, where we said, all right, if you have a compass, it should point in what direction? Well, we say north, but this doesn't give a good picture of the whole field. Let me draw it a little better. Here's the Earth. Maybe I'll make this the rotating axis. So this is the geographical North Pole. And so it's spinning around the geographical North Pole. As you can see, oh, I shouldn't have done this in blue, so I can do my field in blue. All right, try that again. So kind of want to stick to the blue here. So here's the Earth. Here's the spinning of the Earth. We're kind of imagining buried in the Earth is a little bar magnet. Now we can understand this a little bit better. Remember, all magnetism comes from moving charges. Well, it's the hot Earth together with the spinning of the Earth that's going to make the motion of the liquid core of the Earth that's going to make our magnetism. And so we have to have all of those together. We have to have that hot core, we have to have that liquid, we have to have the spinning. Without those, we will not get our magnetism. And so this, as we're showing in the picture, is our magnet. We'll kind of visualize buried deep in the Earth. And so this has a North Pole and this has a South Pole. And so if I were to draw the magnetic field that you would see from the one in the Earth, not the one in your hand. So this is the one in your hand, but the one from the Earth. It should be kind of this blue dipole pattern where it comes from the north and terminates on the south. And so remember, the magnetic South Pole is in the geographical North Pole. And so we would have a magnetic field, and here's what I want to emphasize. We would have a magnetic field actually inside the Earth. You could use a compass to navigate inside a tunnel. Often doesn't work well because there's often most of our tunnels are mines. Most of our mines are in rock that have a lot of magnetism, so it gets overwhelmed by the rock around it and doesn't really work that well. But in theory, there would be a magnetic field in the Earth. And in addition, there would be a magnetic field not just on the surface of the Earth, but above the Earth. So you could use a compass to navigate in an airplane, and that works great. You don't have the other rock around. You don't have to be on the surface. Now, I'll draw the other half just for completeness, but I really wanted you to see that the field is both inside and outside. And I also want you to see the direction of the field. Do you see that the field is not parallel to the surface of the Earth? Take Santa Barbara, for example. So if this is the spinning of the Earth, the equator would be right about here. Santa Barbara would be right about here at a 35-degree latitude north. And if I were to then hold a compass in my hand, or I'll just use this one again, and spin it, notice, of course, it will point north or near north. But do you also see that the magnetic field is tilting inward? So it doesn't really show for most compasses. Most compasses, they just want to be able to rotate in a horizontal plane. And so you just are seeing the horizontal component. But I'm trying to point out there's also a vertical component. This compass would actually like to tilt downward. Now it can't by the way it's mounted. But that's why we have even better compasses. We've got this one here that you can hold like a traditional compass, and this end here will point towards the north. But if I do a little bit of an alignment with the north, and then I give it the freedom to go into the Earth or out of the Earth to what we call a dipping compass. This gives me a better visualization of what direction is the field right here in this room. And so this field is going in to the Earth. It's going north and down. And it's going down quite a bit. And you can see that in the picture. And in fact, what is not really illustrated here, and I wanted to emphasize, is what would happen if I went further north to, say, San Francisco or Seattle. Notice that as I go further north, the magnetic field dips more and more. Here's my point. You tell me how much that dips in, and I can tell you your latitude. Right? And so my compass can not only tell me what is north and which is south, which would be east and west, but I could also tell you your latitude and your location. Now, for you guys in the life science, you might appreciate this more since you are studying other animals besides humans. Us humans, we don't see magnetic fields. We don't sense magnetic fields. But other animals do. Ever wondering how a homing pigeon works? Well, their brains are made out of a lot of iron, and they can sense the magnetic field. And so if you put a pigeon right here, but it was trained as its home in San Francisco, it would go, this is the direction of the field. Where I'm from, it's supposed to dip more. So, time to head home. So they fly. And if they fly that way and it dips less, they go, oh, nope, that must be the wrong way. Well, let's go that way. And then they go, oh yeah, dip more. And they make it to San Luis Obispo, and then they make it further, and they make it further, and eventually they get to San Francisco. And they can actually read and sense the magnetic field. And so they have a magnetic field mapping that gives them the ability to train. A real fun experiment I wasn't part of, but a friend of mine was a part of when I was in graduate school at UCLA. He goes, you got to come here. He was a life science person. He goes, you got to see what we're doing. And I was like, okay. And they were trying to figure out how these lobsters, Caribbean lobsters, migrated. They knew that they lived in the shallow waters during, I guess, the winter months, and then during hurricane season, they would migrate these great distance over open sand, and they could not, how would they know how to navigate? And they began to think that it was probably magnetic. And so they went down to the Caribbean, they caught a bunch of lobsters, they brought it back to UCLA, they put them in a tank about the size of this room, and underneath they put a little magnet. And then they would drop the lobsters down on the bottom, and then the lobsters would just walk directly along the magnet. And so we'd just watch them walk all the way across, and they'd get near the end, and we would go underneath and reverse the magnet and come back up. And the lobster would just like, the lobster actually turns around, starts walking back the other way. And so they just did this for hours. This was their famous research paper. They just watched the little lobsters follow the magnet. It was a clear indication of the magnetic field. Sea turtles, same way. How do you swim in this open ocean for thousands and thousands of miles and know where you're going? Okay, and I don't think the sea turtles is quite as well recognized or how it exactly works. It's a combination, and so I don't know how much that is magnetic, but there is a component of that. At least I think that's the latest theory of it. Anyways, it's really nice then to see that the Earth has this magnetism, and other animals have other sensories that can then pick this up. And so that's the point here. Well, I better keep going here because, as you know, at some point we want to get into the mathematics here. We want to get into the interaction. How do these things interact? How strong are they? And so you can begin to see that we have, again, this interaction. And it is the field effect interaction that I'm trying to get at here with our magnetism. Okay, so now that we hopefully have a visual picture here, let me move on and dive a little deeper into the magnetic field. I guess I would call this section 3 of your book. Oh, and I don't want to use blue. I'm going to say blue for the magnetic field. All right. And so section 3, which is titled The Magnetic Field, is kind of what I already started talking about. What is the magnetic field? Here's the symbol we're going to give. It's B. And so just like we had E for the electric field, we're going to use B. Now, we need to measure the magnetic field in some kind of units. Now, maybe a good sidestep is to come over here and remind you about the electric field. Remember I said that one thing that hopefully will make this chapter understandable is there's a lot of similarities between electric fields and magnetic fields, and electrical interactions and magnetic interactions. A few things that are different, but a lot of similarity. And if you remember, we said the electric field was the amount of force you got per charge. We said the units were newtons per coulomb. That was chapter 18. And it kind of made sense. We like to use the electric field by saying how much force would you get if you had 1 unit of charge. Well, I like to do it this way. I like to say, okay, let's do the same thing with our magnets. Let's take a magnet. So I'll make a magnet, North Pole, South Pole. Let me take and make a magnetic field so I can have something to visualize. Maybe I won't draw too many. Maybe that'll be enough just to kind of get it there so it doesn't look too messy. Let me point out that the field goes from north to south. Let me point out there'd be a field in the other half down here also. And let me just put an electron in the magnetic field, put a circle around it, why not? So there's my electron. And let me start with this. Let me start with the electron not moving. How much interaction would I have between the electron and the magnet? And yes, it is a trick question. Yeah, good. You guys are shaking your head. None, right? Because let me go back to the orange that I was using for the electric field. So surrounding this electron would be an electric field. Electric fields interact with electrical objects. But magnetic fields interact with magnetic objects. And even though there's a lot of similarities, right now I would say there is no interaction between those two. When does the electron become a magnet? Does it ever? When it moves. Right? What's the source of all magnetism? Moving charges. All right. So I would say that this electron, if it is stationary, will not interact with the magnet. However, once that electron starts to move, now it makes magnetism. Now here's the interesting thing. How does it move? And it can move either by translation or rotation. So it doesn't have to move by translation. It could just be sitting there and spinning. And as a side note, all of our electrons are doing that. They are spinning. So I would say even without translating, there is an interaction. There is a magnetic field. However, let me just focus on translation here for a second. I would say then that if this electron then begins to move, maybe I'll draw it in green, with a velocity v, now there is an interaction. All right, so the point of all of this was to point out that it's very easy to confuse electric and magnetic because they are so tied together. But magnets interact with magnetic fields, right? Charges interact with electrical fields. Sometimes we'll have both at the same time. In this case, if we had actually a stationary electron, I would say there's no interaction. But what I want to focus on is let's make it move. Because this is the best way, I think, to explain how we're going to define the the magnetic field. We're going to follow this thinking. We're going to say there's a certain amount of force per charge. Did you have a question?
Yeah, I was a little confused on like if the magnetism only comes from electrons moving, then like why in the ferromagnet is there such a strong charge?
Oh!
I was confused like because you said like they sync up.
Oh.
They're all moving at the same rate.
Okay, not so much at the same rate, but the same direction. Okay, so again, the reason this becomes a magnet and the other one is a permanent magnet, I lost it, but I'll grab this one. It's hard to see moving charges in here, but they are. Because there's always electrons orbiting around the atom. That's what I was trying to get at earlier, is that all magnetism comes from moving charges. And so when you take an atom, you're going to have electrons moving around. And so even though this is not hooked to a power supply, which would make it easy to forget that there is moving charges, there are moving charges because they're orbiting around the atom. And if you just have them in a random direction, some go left, some go right, each of those individually makes a magnetic field, but they cancel each other off.
So the only difference is like that one was synced up while it
right.
While it was melted.
Right, it was cooled. And so these are all synchronized, I'll just say, in a clockwise direction. So these are all going in a clockwise direction. But they are definitely moving. Got to have moving charges. It's moving charges that makes our magnetism. Yeah, and again, so that's why I'm pointing out here that there would be no interaction if this thing was stationary. And that's important to understand, because if we come over here to talk about the strength of the magnetic field, here's how we're going to do it. We're going to say that the strength of the magnetic field is the amount of force you get per coulomb. And here's why magnetism gets harder. Per meter per second. Right? You don't get a magnetic field unless it is moving. So you're not going to get a force unless there's moving. So that's what makes magnetism one step harder than the electric field. So the electric field was defined as how much force would you get per unit charge. So we'll start off with that. We'll say the definition of a magnetic field is to say how much force would you get if you put a unit of charge there, but only if that unit of charge was moving at a rate of 1 meter per second, because magnetism depends not just on how much charge, but how fast it's moving. So you got both of those. And it gets worse. It's how much is it moving perpendicular. Ooh, now perpendicular to what? Well, let's hold off on that question for just a second. But here's where, like I said, it gets uglier, if you will, because there is no interaction unless there is a movement perpendicular to the field to get a force. All right, let me build up on this, because this is tough to get, but at least it'll answer this question. It'll answer the question of what is the unit? And the unit for the magnetic field then would be a Newton per coulomb per meter each second. Now, you might even group some of this together to make it look more like electronics. You might put the coulomb per second and call it an amp. In either case, we are going to give Tesla the honor, and we're going to call it Teslas. And so capital T we will use to measure the magnetic field. And so capital T is a unit of Tesla. But to understand what a Tesla is comes back to understanding where you get magnetism. You get it from a moving charge. There it is. It's how much force do you get when you have 1 coulomb of charge moving at 1 meter per second. And so that's our definition of a Tesla. Now, I will be quite clear, hopefully, that 1 coulomb of charge is a lot of charge. Actually, 1 meter per second is pretty fast for charges that are moving in a wire. I guess for one individual free charge it wouldn't be, but for most charges, this speed of 1 meter per second is huge. This charge of 1 coulomb is huge. What that means is 1 Tesla is ginormous. So most of our measurements will be much, much smaller than Tesla. We'll be doing millitesla and microteslas. It's why what is sometimes referred to as the practical unit is called a Gauss. And again, in honor of another great scientist working in this field, Gauss. And so don't be surprised if you see the symbol capital G for a Gauss. 10,000 Gausses make 1 Tesla. But the SI unit is a Tesla. So mostly we use Tesla, and then we use the prefix like milli, micro, and nano. Just say, okay, that's the fields are 1 Tesla is it's not unreasonable, it's just a very, very strong field. Now, let's come back to this. What do I mean by this perpendicular? Well, if I were to draw, and maybe I'll keep this a little simpler here, and say, all right, here is my, let's go to the red. So here is my electron. It's moving this way. And so my velocity is v. What direction is the field from, say, this magnet? Now, in this picture, I kind of got it going in the same direction as the motion. Maybe I'll keep that for a moment. Then we'll do an example here. Maybe I'll have the magnetic field going this way. But what this equation is trying to say, the amount of force, the amount of interaction then between these two magnets. So notice I'm calling the moving electron a magnet now. The amount of force I could calculate, and what I will need to know is the charge, the strength of the field, and how much of the velocity is perpendicular. And so if I were to take the velocity and make it, part of it is moving parallel to the field and part of it is moving perpendicular to the field, it's only the part that is perpendicular to the field that is relevant. And that is what's going to make magnetism hard. It means that we need to do this. I'll try to make the math a little bit easier by saying, let me put in sine theta, because this over here, v perpendicular, would actually be the velocity v multiplied by sine theta. And so I think this is easier to understand and to calculate if we write it this way. The strength of the field is the amount of force per charge times the velocity times the sine of the angle that is between the v and the b. And that way I can just write in whatever the v is. I don't have to then go, okay, I need a component. But that's really what that sine theta is doing for me. That sine theta is giving me a mechanism to say, okay, what is that angle? In fact, I think this equation is best written without a quotient. And so this would be Q V B sine theta. And I finally get to our first math equation for today. And that is, how much force would be on a moving charge in a magnetic field? Now let me emphasize, right? You have to have a moving charge to interact with a magnet, right? Because a charge by itself is not a magnet. It's got to be moving. But once it's moving, there is going to be an interaction. And this is our first formula. To figure out how much force is on a moving charge, you need, of course, how much charge do you have and how fast it's moving and in what direction. And then you have to say, what is the strength of the field? And when you put those four things together, you can now tell me mathematically how much force do I get. All right, well, if that wasn't hard enough, there's one more. What direction is that force? Remember I said there was a lot of perpendiculars here? The direction of the force is actually then perpendicular to both the direction of the velocity and the direction of the field. Whoa, look at this picture. What direction is that? What direction would be perpendicular to both the velocity and the field? And if you're thinking two dimensions and looking at the whiteboard, you're in trouble. because perpendicular to both of them is out of the board, straight out. It's why I got this crazy thing. If I put this black one in the direction of the velocity, and the white one, well, there we go. And the white one in the direction of the field, do you see how this arrowhead right here is perpendicular to both of these? You got to think 3 dimensions in this. This is why your author's pictures are going to be so much better than mine, because you have to do a V cross B. Now, here's some good news for you. Your author has given you a nice little picture here to help you. And his technique's a little different than mine, but I'm going to use his, because this is not so easy. He calls this right-hand rule number 1, which you can imagine there's a number 2 coming. All right? But to help you out, take your right hand. And this is important. It's got to be your right hand. And most people are right-handed. So during the test, when you're writing and you want to get the direction, put down your pencil or a pen, whatever it is, and get your right hand. And if you hold up your right hand, if you put your thumb in the direction of the velocity, and then your fingers in the direction of the field, so if you can align your right hand, your palm will then be the direction of a positive force, a positive charge, and the back of your palm will be the force for a negative one. Okay, so in my picture, I would take my right hand and go VB and say it's a negative, so the direction is out of the board. So this thing would go like that. And that's what your author is trying to show you here. He's saying, look, take your thumb, call that V. Take your fingers, call that B. Adjust the angle between your thumb and your fingers. That's the theta. That's the angle between the V and the B. And then your palm will be the direction of a positive, and the back of your palm will be the direction of a force on a negative. And so again, very, very three-dimensional. Very hard to visualize. The force is perpendicular to the plane of both V and B. Okay? And so you have to do 2 steps in this problem. The first one is you've got to calculate the amount of force. So you've got 4 factors to add up or multiply up. That's hard in itself. But the second thing is to figure out its direction, and that's where this right-hand rule comes in. Well, that's pretty complex. So because of that, this is probably a good time to do an example here. Let me go to the end of the chapter here. It's a long chapter. Maybe I better talk a little faster. But somewhere in here, I want to do number 2, because I asked you on the homework to do number 1. And so I'm going to do number 2 here with you. So what does number 2 say? Number 2 says, repeat exercise number 1, but use a negative charge. All right, so looking at this, I'm going to say, here's my right hand. The question just simply says, what direction is the magnetic force? And number 1 says on a positive, but I want to do the negative. All right, so your thumb goes in the direction of the velocity. Your fingers go in the direction of the magnetic field. Now let me make the picture a little bit bigger, and let me use this as an opportunity to show you a nice notation we like to use. Do you see the little dot there? Here he's saying magnetic field, and he says out. See the circle with the dot? That is supposed to be a arrowhead pointed right at you. If I took this arrowhead and pointed it right at you, that's what you would see, an arrow with a dot. Hopefully you've never seen an arrow coming right at you, but that's probably what it would look like. And so, look at this one over here, a circle with an X. What's that? Yeah, that's the arrow pointing away from you. That's what might be the feathers on the arrow as it shot away from you. Okay? So, what we're saying here is if I put my right hand in the direction of V, so my thumb in the direction of V, so I guess I'll do that, and my fingers in the direction of B, so that's towards you, so there I have my right hand. The force on a positive would be this way towards the negative x-axis, and a negative would be towards the positive x-axis. And say, what are we doing? We're repeating for a negative, so it would be to the right. So this particle would go to the right. Let's try B. I would put my thumb up and my fingers right, and I'm after a negative charge. That's the back of my palm, so that would come out of the plane. It would go that way. That would be the force on it. Oh, sorry, it's moving this way, so it'll go out. Well, let's do this one. So this one, let's see, I got V that way, but I need B in. Okay. This is always fun to watch on a test. All right, so V that way, B that way, and then my palm, my back of my palm is down. So this thing right here would go down. D's an interesting one. So I got V this way, and I got B that. You can't do it. That's because the force is 0. Sine of 180 degrees is 0. Okay, so 0 force. Because remember, it's how much force is perpendicular to the field. I mean, sorry, how much velocity is perpendicular to the field. None of it's perpendicular. All right, so this one, let's see, the velocity is in. So, see, velocity is in. Field is up. Okay. Back of my palm is this direction. So this one would go like that. This one, the velocity is out. The field is that way. Back of my palm is up. So this one would go like that. All right, so that's our little trick. And maybe that's a good start. Now, let's try 4. Why not? If you'll notice on all of those, they gave us V and B and we looked for the force. But did you notice, really they only have to give you any 2 of them and you can find the third. So in this one, it says, repeat this for a positive charge. Okay, so remember the force is in the palm. So if they give me the force up, I'm going to put my palm up. And the field is out, so I'm going to put my right hand out. And so my thumb would be the velocity. So the velocity would be this way. And I think that was the question. Repeat. It says, what is the direction of the velocity? And then 3 says for a negative one, and we're asked for a positive. So this one here, I would put my palm up and my fingers right, and so my thumb is pointing out. So the velocity would be out. This one, the force is left, so I'd put my palm left. I would put my fingers in, because that's the field, And so my thumb is up, so the velocity's up. And so there's right-hand rule number 1. Don't to be confused with number 2. Okay? And so that's how we're going to do our calculations. Well, it is time for a break, a well-deserved break. There was a lot of information, and we got a lot to go. So I will say, let's take our 15-minute break. Let's come back at quarter till. Let's do a 14-minute break, and we'll teach you 1 minute, and then we can get started, make sure we get it all covered. All right, see you guys in 15. All right, well, welcome back. We'll jump right in here because there's a lot to cover here. I want to see how far we can get and do as much justification as we can, and hopefully I won't have to rely on adding a supplemental part to the lecture, but I might have to do that. Now, this is a good part now to go on to the next section, which is section 5, but I'm going to incorporate that with section 11 because both section 5 and section 11 talk about an application. And so if you remember before the break, we learned that there would be a force perpendicular to the motion, but let's extend that a little bit more. And that's what he's doing in this picture. So in picture 20 here, he says, oh, watch this. Let's say we have a moving charge. And in this case, notice he says a negatively charged particle. Okay? So why don't we just take it at this moment. And I'll take my right hand, and I'm going to put my thumb in the direction that it's moving. I need to adjust my hand so my fingers go in the direction of the field. And the force on a negative would then be the back of my palm, and so the force is here. So what that would do is curve it over. Now, watch what happens when the negative gets here. Notice that the force is always perpendicular to the direction it's traveling. So I would then have something that would look like this, where my thumb would point to the right, my fingers would point in, and the back of my palm would point down. And then notice it's always pointing inward. In fact, hopefully this reminds you of the chapter we did on circular motion. I think it was chapter 6 back in Physics 110, where we said if you always had a force perpendicular to the motion, it would go in a circle. So let's put those two together. Let's put what we just learned for magnetism together with what we learned for our mechanics, and when we put those two together, it would tell us that if you always applied a force perpendicular to the motion, it would go in a circle. And so what your author says here in applications, he says, all right, going back to Physics 121, we could put Newton's second law here. And in this case, the net force would be QVB, and I'll put here sine theta for just a second. But we also learned it would go in a circle, so going in a circle would have an acceleration of V squared over R. Now, for this particular one, they deliberately set it up so that the motion was always perpendicular to the field. And so notice the field is going in, and of course notice also the field is in, but notice the motion is in the plane, so that's always perpendicular. And so we could then, for this picture anyways, call this the sine of 90 degrees, which, well, I shouldn't have put it that way. This is 90 degrees, and that's just equal to 1. And so this reduces down to QVB equals to mv squared over r. I guess even a v cancels off, but you might be curious to know what the radius is, and this would be our answer. And so I'll call this another formula for the chapter, but hopefully that's not coming across as a new formula. That's nothing more than applying this new force, the magnetic force that we've learned about, and applying it to our mechanics, and we put that together and we say this then would be the radius. And so your author says one thing neat about magnetic fields is they would make charged particles move in a circle. Now, how can that be useful? Well, why don't I jump quite a ways first towards, I don't want to take too much time here. How far is it to the section 11? But one of the most obvious applications is what is called cathode ray tubes. Cathode ray tubes are just a fancy way of saying you've got an electron beam, an electron gun. And so if you did something like this, if you kind of remember from a couple chapters back, we said, what if you took a plate and made it positive and another plate that's negative, and you put an electron in here? Wouldn't that accelerate the electron? And if you made a little small hole, it would go shooting out. And we talked about how this would shoot electrons. And so now these electrons would be traveling. Well, what's nice about a cathode ray tube, maybe I'll just call it a TV or an old school TV, is that the electrons start back here, they go shooting forward, and when they hit the screen here, they give off light. Now that's an interesting set of physics of why a hitting electron, hitting phosphorus gives off light, and we're going to talk about that in the modern physics section. So coming up in a few weeks, we'll talk about that. So what I've done here is I've turned on an old-fashioned TV screen. It's shooting the electrons out. However, notice they don't just hit in one spot. And that's what this picture is trying to say. It says, okay, you go shooting the electrons out, and then right here, there is a magnetic field. Now, they show a current, and so the current makes the magnetic field. And what we can do is control where that hits. Let me change my point of view to the front. And so here's the screen. And so with a bunch of current, what we can do is take this electron beam and we can deflect it up into the top corner right here. And then by changing the amount of current here, the current's making the magnetic field, we can change how much deflects, and we can then shoot the beam here, and then 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 here, and go all the way across. And then we can go all the way down, 525 lines if you use an old standard definition television. And so the way an image is actually made is these electrons hit the screen, hit the screen, hit the screen, and they go all the way across the screen, they go all the way down, they go 525 lines, and they eventually make a bunch of bright dot spots where the light hits. And that's your image. And so that would be one frame of your movie. And so if that electron beam can scan all the way across and do that in 1/30 of a second, then it can start over again and make another image 1/30 of a second later, and then make another image 1/30 of a second, and that's what motion is. That's what a video is. And so when you're watching the TV screen, you're watching a series of pictures 30 times a second or 60 times a second for better quality, and they're just flashing it up there. And the way they make the image on the screen is by controlling where the electrons hit. And what I'm trying to say is how you control the electrons is with a magnetic field. You bend them down, you bend them left, and so you have some currents left and right, you have some currents up and down, and so the electron goes shoo, 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 and it just scans across. And to kind of show you that neat effect, we can mess with these electrons because I have this big magnet that has a big field. Now, you might want to remember what we said before the break, what this field looks like. And it's this big arching field like this. So if the electrons are coming this way towards the screen, I would probably get the most effect if I make the field like this. If I bring it off to the side here, I will deflect them away. They'll go, phew, they're going over there, or over here. Oh, wait, now I'm pulling them towards me, so let me do that. Put them away. And so this is my deflection. Or a fun one to do is, remember this field, goes north to south, okay? And what if I put it this way towards the screen? So the electrons that are coming right towards it would actually going parallel to the field. Remember we talked about that would be zero force. That would be sine of zero. There's only a force when they're perpendicular. So that's why I did this, and I was saying, look, this will give me lots of force. This way won't give me much force. Now, it's a very complex field, but it goes like this. And so what ends up happening is they would make circles around the field. And so sure enough, if I put this in here, can you see how they get all deflected except for the ones coming right for this pole? It's kind of hard to see because the magnet gets in the way, but see how there's a little circle right under here? Right there. And that's because the electrons don't feel a force when they go directly in the direction of the field. And when they're off, they go in circles around the field. And so that's why your author, well, if I can go all the way back, I'm going to go back and forth here a couple times. But your author says this is kind of the path of what you would get if you put a bar magnet in front of a cathode ray tube. They would come out and then they would start to make coils. They would make circles around the field. They would follow the field lines. They would be kind of trapped in there. And so these magnetic fields become a great sense of technology into how do we trap these little charged particles. And in this case, this would trap them and make them hit the screen right at where the pole is. Your author says this is, of course, how the northern lights work. Because remember, the Earth has this big magnetic field. So remember, the north pole of the magnet is in the geographical south pole. So the Earth's magnetic field comes out and goes around. And so this is the field. And if charged particles that are coming from our sun and the cosmos come in, they get trapped and they go circles around that field. Now the good thing is they don't come in and hit our mid-latitudes where we are. They get trapped in the field and they circle around, and they're going to come in at the North Pole or come in at the South Pole. And just like this screen, when they come in, they're going to hit the atmosphere. And when they hit the atmosphere, they'll give off light. And so in the North Pole or in the South Pole, we have what we call the northern lights and then the southern lights. And that's, of course, the picture your author put right here at the beginning of this chapter right here. Here's a photograph of the northern lights. And so the sky is just aglow because it's getting hit with these charged particles. These charged particles then were trapped, and so our magnetic field from the Earth becomes kind of a shield. It becomes a protection. That's a problem with Mars. Mars doesn't have an atmosphere. It doesn't have that protection. And so these particles come in and they just rip off the whole atmosphere. And so whatever atmosphere Mars might have had when it had a liquid core, when it had a magnet, now it's no longer a magnet. Its core is solid. It's a dead planet. And because it doesn't have a magnet, it can't protect itself. It can't shield itself from these charged particles, and the atmosphere gets ripped away. And so there's very, very, very little atmosphere on Mars or on the Moon. Each of them are what we often call a dead planet because they don't have a living core. They don't have anything making a magnetic field. They don't have anything shielding them from these fast-moving particles out there. Now, with all that said, later on, when we get into modern physics, we're going to talk about nuclear fusion. And we're going to separate nuclear fission from nuclear fusion. And it's going to be real important. We say that there's two ways to use nuclear energy, and nuclear fusion being very different than what we do right now, which is nuclear fission. And so if we get nuclear fusion going, and so you'll listen to that lecture later on here, but one of the things is we got to trap these particles. And so to make it happen, we warm up a bunch of gas to be the equivalent temperature of the center of the sun. Actually, we want to get hotter than the center of the sun, but that's a whole other story in itself. But how do you trap these things? And the good news is they're so hot that when they bump into each other, the electrons just fly off. And so they have charges. And you can control where charges go by a magnetic field. And so we put them in what's called a toroid shape, a donut shape. And so that's what this is trying to get at. And so here's the design, here's the research being done on how to make the energy basically the same way the center of our sun makes energy. And so we're getting closer and closer each decade, but as the funny story goes, we're only 10 years away. And we've been saying that for 50 years. So someday, maybe we'll get there. But it's a tough technology. Going back to section 11, here's another fun one to do. This one is then separating two materials, and this is a good example I want to do in the book here. But what if you have an ion, some kind of charged particle, coming towards an opening, and then there's a magnetic field? Now, let me come back over to this equation. Remember, we said when you hit a magnetic field, you're going to go in a circle. Now, this one is set up to only complete half a circle, a semicircle. But as these charged particles enter in here, they will then curve, and notice that the radius of this curvature depends on how much mass they have. So we call this a mass spectrometer. This is a perfect way to figure out what you have. How many, say, oxygens do you have, and how many nitrogens do you have? They weigh different. So maybe, maybe we're in organic lab and we make this compound and we want to know, what did we make? How many oxygen atoms does it have? How many nitrogen atoms does it have? And there's many ways, like the spectrometer that you guys probably actually use if any of you done your OChem yet. But another way is called a mass spectrometer. And what you do is you take your unknown compound, you put it in a furnace, you heat it up until everything separates apart into oxygen, nitrogen, and carbon, and you shoot it through this mass spectrometer. And what ends up happening is they go through and they curve different radii. And so right here, you would get your lightest masses. And so if we're doing an organic compound, our carbon would show up here, and we'll collect how much carbon we have. Then we'll also have another little bucket right here, and we'll collect how much nitrogen we have. And then we'll put another little bucket here, and we'll collect how much oxygen we have. And so now we can have an empirical formula that says, I have this many oxygen for this many carbon for this many nitrogens. And I can separate those out. In fact, the problem we'll do is we will use it as a separation of things that can't be separated chemically. This probably would be overkill for separating oxygen and nitrogen. Sometimes it's needed, but you can usually do those chemically. But other things, you can't separate them chemically because they behave exactly the same way, but they have the same mass. And so that's more appropriate for what this is for. So here's what I'm going to say. The first thing that you will notice is for this to work and separate them out, they got to have different masses, but they need to have the same velocity. And so what is called a velocity selector happens first, and that's what this area is. If you'll notice here, look how this is set up. You send an ion through here. Did you notice that they were showing the parallel plates? Well, let me go back a couple of chapters. So this plate is positive, this plate is negative. Let's just say I have a positive shooting through here. If I have a positive shooting through here, notice that it would be pulled up towards this top plate because the top plate is negative. And so your author is calling this force QE. And so I would say I have an upward force. So I'll say force up is QE. But if you'll also notice, the magnetic field is there, and there's a downward force. Well, let's use our right hand again. So the velocity is this way. The magnetic field is towards you. My palm is down, and so a positive charge would be pushed down. And it would follow this equation, QVB. QVB. Now, if those two are exactly equal, they will go in a straight line. And so this green line is showing the direction of the particles that have what I'll call the magical speed. You see, if they're going too fast, the magnetic field dominates and they angle down and they don't make it through this hole. If they go too slow, the magnetic field's too weak and they go up. Remember, the magnetic field is related to how fast they're going. So hence, this is why we call this a velocity selector. We can know that every particle that makes it through this hole has to be going the appropriate speed. What would be the appropriate speed? Well, here, well, maybe I'll erase this picture. But the appropriate speed would be when those two forces exactly balance. So when QE equals QVB, Q's cancel off, or to put another way, for any particle that has the speed that's equal to the ratio of the electric field to the magnetic field, those are the ones that would actually go through. Anything going too fast doesn't make it. Too slow doesn't make it. It's what we call the Goldilocks speed. It's got to be just right. Not too fast, not too slow, just right. And then that one goes right through there. And now once you know the speed, you can then come over here and say, what is then the radius? And you'll know then where different massed objects would be collected, and then you can decide which ones you have. Well, I better move on because there's a lot of different really good good applications here, but I do want to do some examples for you. So let me try number 12 first, and I think the 21's the other one here, but let's go down a couple pages here to the problems and try number 12. So number 12, I can actually do some numbers here. It says a cosmic ray electron moves at a speed of 7.5 times 10 to the 6 meters per second perpendicular to the Earth's magnetic field. So this is what I was saying about the cosmic rays, the aurora borealis, the fact that the rays are coming in from the sun. These particles are coming in from the sun. Some of them are electrons, some of them are protons. They're coming really, really fast, and they're going to hit this Earth's magnetic field. Unfortunately, we have that there as a little shield. This is the strength of the field, 1 times 10 to the minus 5 Tesla. What is the radius of the circular orbit that these electrons would follow? Well, fortunately, we already did the mathematics. The mathematics is saying, take this equation right here, because this would be the magnetic force, QVB, and then sine of 90 degrees. Set it equal to mv squared over r, and then, of course, you would get this. And so number 12 says, let's actually get the radius. So we need the mass, we need the velocity, we need the charge, and we need the magnetic field. All right, so I'll start with the mass. They said it's electron. I know that the mass of electron is 9.11 times 10 to the minus 31. And so kilograms will be my unit. That'll be my base unit and my main unit here. And so there's my mass. My speed, what'd they give me? 7.5 times 10 to the 6th meters per second. So that's the speed. The perpendicular to the Earth we already took care of when we said sine of 90 degrees. The strength of the field is the 1 times 10 to the minus 5 Tesla. And the charge is the 1.602 times 10 to the minus 19 coulombs. Well, let me do my numbers and my units. And so my numbers. Did I misplace my calculator? I'll have to, well, let's do TI-84 app. Okay. All right. So, I know I had that calculator. I guess I was playing with it on break and I lost it. I think I left it in the back room. All right, so 9.11 times 10 to the negative 31 times 7.5 times 10 to the 6th divide by 1.602 times 10 to the negative 19 and divide by 1 times 10 to the negative 5. And so I get a number of 4.26 24, okay. Times 10 to the nothing, okay. And then my unit should come out in meters. Let's give this a try here. I'm going to put my units here as kilogram meter per second, coulombs, and this will give me a chance to talk about the Tesla again, right? Remember, the definition of a Tesla was how much force, newtons, do you get from 1 coulomb of charge moving at a speed of 1 meter per second. And if I simplify all of this, I guess coulombs would cancel off, and I will have kilograms meter per second here. Let me put the Newton down here. Let me flip and multiply this. So this is going to be a second here and a meter up here, which is perfect because right there the kilogram meter per second squared is the Newton. So those together is a Newton, and we're left with meter. So sure enough, it comes out in units of meter, as I would expect. Oh, let's try 21. 21 was me talking about, again, that mass spectrometer. Here it says a triply charged uranium-235 and uranium-238. Well, let me start right there. They're both uranium, and something that you may or may not know yet in your education is that you can have the same elements, but they have slightly different masses. Those are called isotopes. Maybe I should leave this equation here just in case. But isotopes are tough to work with because chemically you can't separate them. They have exactly the same properties. So how do you separate something that's uranium but lighter from uranium that is heavier? You got to do something involving mechanics here. And this is a perfect opportunity to send it through a mass spectrometer and separate the uranium-235. So what they've done is they said they've taken off 3 electrons. That's why they say triply charged uranium-238 and uranium-235 and 238 are being separated in a mass spectrometer. The much rarer uranium-235 is used as the reactor's fuel. So we're trying to make some nuclear fuel here to run our electricity grid, and we need to separate out uranium-235 from uranium-238. They give us the masses of each of the ion, and they tell us that it goes through some kind of velocity selector. They don't make us figure out the speed, so I guess I don't need this part of the mass spectrometer, but they send it through a velocity selector, and they give me this speed, 3 times 10 to the 5, and then this is the field, a pretty strong field, 1/4 of a Tesla. What is the separation between their paths when they hit the target after traversing a semicircle? All right, so what's going to happen is if this is the opening, the uranium-235 is going to hit here, and the uranium-238 is going to hit with a little bit further. And so notice that we are after the diameter of the circle, not just the radius. And so if we say, how do you get diameter, which is twice the radius, we would have 2 mv over qb. So how far apart are they? Well, let's call the difference between them delta d for the difference between the 2 diameters. And so delta d would be diameter of the big one minus the diameter of the small one. Okay, so as they fly in a circle, I'll just take the difference in their diameters. So this would be a 2 mv over qb for, I'll call it number 2. And this would be 2 mv qb for the lighter one, number 1, uranium-235. Now, fortunately, They each have the same velocity, so there's no point in calling it velocity 1 and velocity 2, right? They went through that velocity selector I talked about. They're each triply charged, so they each have the same Q, so there's no point in calling it a Q1 or a Q2. They both go through the same spectrometer, so they're both exposed to the same magnetic field. And the only thing that would be different would be M2 and M1. And so this is the mass difference times all of this. So then I can put in my numbers. So it's 2 times, and what they give me for the velocity of this thing? 3 times 10 to the 5. So 3 times 10 to the 5 meters per second. Then we have the difference in their masses. They're both 10 to the minus 25, but we've got the heavier one at 395 and the lighter one at 390. All right. So there's the difference in their masses. The field is 1/4 of a Tesla, so I'll put that down here, 1/4 of a Tesla. And the charge, as they said, is triply charged. So you've ripped 3 electrons off. So it would be 3 times 1.602 times 10 to the minus 19 coulombs. Now, since I already did the units on the last problem, I'll just go ahead and say the units come out to be meters. Grabbing my calculator then, I will start here with this difference, because that is a 0.05 when I subtract that, times 10 to the negative 25. Then times 3 times 10 to the 5, and then times a 2. Then divide that by a 3, divide that by 1.602 times 10 to the negative 19, then divide that by 1/4, and so they are separated by 0.025 meters, to 3 significant figures. And so our little collecting buckets, I guess that's 2.5 centimeters, 1 inch, right? 2.4, is it 5.4? 2.54, yeah, is 1 inch. All right, so this is basically 1 inch. And so our collecting buckets are pretty close together here. Which I think is why then your author goes on here and says, discuss whether this distance between their paths seems big enough to be practical and to separate uranium-235 from uranium-238. And I think that seems big enough. It's not that big, but we can measure things really accurate. But remember then, there's going to be always some uncertainty in these things going on. And so your collecting bucket, you're trying to collect the 235, there's probably going to end up with some 238. Which is, if I understand the technology right, this is why they run it multiple times. So they run it through, and they collect a bucket of 235, but it's only half 235, and the other half is, 238. So they run it again, and each time you run it, you get a higher percentage of 235. And eventually you get 235. It's what we call enriching uranium, and of course, to make nuclear weapons, you have to run that many more times compared to nuclear fuel. And so there's a different grade in there, and that's why we have all these international treaties on saying, okay, you can do it so many times to get uranium rich enough to make a nuclear power plant for peaceful purposes, but not so many times that you can make nuclear weapons out of it. But this is how they, like I said, enrich uranium. All right, well, let's keep talking, because I just want to do as much as I can and to say, okay, what do we see here with this magnetism? Like I said, your author tries to do an incredible lot here and show you some really neat things. The next one is what we call the Hall effect. Watch this for a moment. If you study real closely these moving charges through either a wire or through, well, maybe a good example for you guys would be the blood flowing in a living tissue, because it has a lot of ions, it has a lot of sodium and chlorine ions, and so these charges are flowing. And so if you watch something like this, and so this was discovered by Hall, so we call it the Hall effect. But the Hall effect basically says, and this is kind of like the velocity selector we were just talking about, maybe you might call it the velocity selector in reverse. But I'll pick on A here at the beginning. But he says, let's look at these moving charges as a current, a total current. And a bunch of charges added up with a velocity is a current. And so because A, we're low on time, and B, because I think your author does a good job of it, so I don't necessarily need to, your author says you can replace all these charges and all these velocities here with a current and a length. And so I might say that this equation and this equation are the same thing, but sometimes it's better to look at the amount of charges by saying we have a length of charge and the whole thing's moving. And so instead of looking at individual charges flowing, he says, let's look at them collectively. Now, both of these are kind of saying the same thing, but it gives me a chance to say, let's just look at the current. But I will point out, remember, the current is the direction of the positive. So remember that right-hand rule we were talking about, right-hand rule number 1? I would say the only thing that I'm changing now is my thumb, instead of being the velocity, my thumb is now the direction of the current. Because that's what we mean. The current is the direction that the charges flow. That was our last 2 chapters on what is current. All right, so taking what we learned in the last 2 chapters, what is current, your author says, watch this for a moment. If you have a bunch of current going this way, so here's the current going that way. If you looked at the individual particles, if they were positives that were moving, they would go this way. And I guess that's what this one is showing. If positives were moving, they would be going this way. If negatives were moving, they would be going this way. And so Hall was the genius who actually kind of figured out what's actually moving. Are the negatives moving or the positives moving? Because as I said, if negatives go this way, that gives you a current this way. If positives go this way, it gives you a current that way. And so if you only focus on electronics, you can never figure out what is moving. But when you throw magnetism into there, and this is the Hall effect, he says, watch this for a moment. If you were to take positives that are moving, I'll start there, and you put your thumb in the direction the positives are moving, and you put your fingers in the direction of the field, so these little dots are the field, the positives would be pushed down. And what would happen is the bottom of the wire would get positive, and the top of the wire would get negative. But this is the reverse. If negatives are moving, so I'll put my thumb in the direction the negatives are moving, I'll put my fingers in the direction the field is moving, and since they're negatives, I'll use the back of the palm. They would go down, and the bottom of the wire would get negative, and the top would get positive. And so Hall realized that this is an experiment to figure out what's actually moving in a wire. Because I'll say it again, if positives were moving, the bottom of the wire would charge up positively. If negatives are moving, the bottom would charge up negatively. And so you can then just take a voltmeter and measure the voltage between the top and the bottom of this wire. And to see, do I have at the bottom of the wire, do I actually have positives or do I have negatives? And of course, I think you already know the story since we said it. Hall discovered that the negatives accumulate down at the bottom. And so because of that, we now know that it's the negatives that are moving, not the positives. And of course, I've been saying that from the beginning here, but that's what's called the Hall effect here. Now, let me scroll down here. Here's a better three-dimensional picture of his experiment and some math here, but here, well, I'll come back to the math, but here's what he says then. He takes his little probe and he gets the top of the wire and the bottom of the wire, and like I said, discovers the bottom of the wire is the negative, and so there it is. That's the amount of voltage you get. And of course that comes from our velocity selector. Now I'm debating on how much time to spend deriving this equation, but I guess it wouldn't be too much. Remember that the field pushing the electrons down would be QV, and pushing them up would be QVB. And if you think of the electric field, then, and I guess I'll cancel that off, but if you take the electric field and you multiply it by the length of them separating, and when I say length, I guess it would mean the diameter here, and so that's what he says here, L. And so he says here, put together last chapter, or I guess 2 chapters ago, maybe 3 chapters ago with our electronics, this would be then the voltage, or what he's going to call script E, the EMF. So for us, I'm just going to put it over here, and I debate if I should have taken the time to derive that, because he does a good job with that, but he says, look, because of the Hall effect, if you have then a current that is now moving in a magnetic field, there's going to be a voltage across there. And that's its value. And so maybe this would be a good time to do yet another example. How about number 24? And we're going to call this then the Hall effect voltage. Where's 24? No, I'll tell you what. So, since we're going to run out of time, and I can show you how to do this one on a video, let me do a supplemental video, and I'm going to do number 24, okay? So you can see that. But there's some other things here that I can't show you from my home or from my little desktop. So I'm going to say, I'm going to send you a video on number 24, so that's the Hall effect. But I want to continue on and demonstrate what started this discussion, and that is a wire with a current is really essentially moving charges. And so I started this discussion with the Hall effect by saying that you can have a force on a wire just like you can have a force on an individual charge. And that's what I want to show you here. Your author refers to this as section 7, but it's a good example here because as you saw me earlier, I have a wire and I have a battery and I have what we call a tap switch. And when I touch this, there's an enormous current that goes through here. And I use that to show you that that enormous current would make a magnetic field. But I now want to use that as an opportunity to show you that a wire with a current in a magnetic field would have a force on it. So let me take this big strong magnet. Now from your distance you probably can't see, but this green says south pole. So the field is north to south. So I'm going to place it right here. And I want you to keep in mind, then the field is going from the north to the south. Because I'm going to then take this wire and lay it in the magnet. Now from your distance you can't see the plus on here, but maybe you can see the red wire. And so when I tap this switch, current is going to be going towards you. So let me use right hand rule number 1 here. All right, so I'm going to put my finger or my thumb in the direction of the current. I'm going to put my fingers in the direction of the field, and this palm will give me the direction of the force. So the current is towards you. The field then is that way, and my palm is up. So this should make an upward force. And of course I deliberately put it on here so that the force would be up and would lift the wire. Ready? 1, 2, 3, lift. And so that's worth seeing again. 1, 2, 3, lift. And it applies a force. Now it's kind of boring, but if I turn it around, I would then have the current towards you, the field that way, so the force would be down. So you'll watch it go down, down, down. Of course, if I also turned the current around, now I have current going in, field going that way, palm up, jump. And so there is a force on this wire. And we can calculate it based on this formula. And in fact, I think in my notes here I have, hey, this would be a good time to do example number 32. So for you guys, I'm going to say, hey, I'm going to do number 32. I'm just going to do it later this evening and send it to you. But I want to be able to show you the jumping wire here. Now, section 8 gets even better. Section 8 says, look at this picture. What if you did something like this? And this little picture is my little model here. But as you can see, your author has a north pole and a south pole, so there is a magnetic field going from north to south. And so I have kind of the reverse, oh here, there. And so I've got north going to south. And then your author says, what if you took a rectangular wire like this and put it in here so that the current would go up, across, and down? Now, here's why that's relative. He'll be my wire. Look at the current going up. So, again, my thumb goes in the direction of the current, up. My fingers go in the direction of the field. My palm then is inward, and so what happens is this wire is going to be pushed inward. And that's what your author's trying to say right here. This wire is pushed inward. But what's interesting is the other half of the wire on the other side, because there the current is going down. And so on this side, the current goes down. So if I were to take my thumb and point it down, with my fingers still pointing to the right, my palm is pointing out, so this wire is being pulled outward. And again, that's what the author is trying to show right here. And so this great invention is the invention of the electric motor. This is saying that if you were to take a magnet and a battery with some current, the current goes this way, pushes that wire in and pulls this one out. It twists the wire, it spins it. Now there is a little subtlety here. And you can probably see it in this commutator. They don't really show it in this picture, but if that's all you did, it would go over halfway, and then here it would be repelled back, and it would just kind of bounce back and forth. And so what they do is they break contact down here, and now the current starts to go up this side. And so this thing would just keep spinning around and around and around. And so that's how the electric motor works. And in fact, to kind of illustrate it, we thought it would be useful to build a very simple one so students can see how it operates here. So here's my wire. You can just see all we've done is taken some copper wire and wrapped it around a piece of wood, and we drive 2 nails in it. And we put the 2 nails on this little eye hook thing here, and of course it can quasi-spin. And so if we do 2 things, we get a set of magnets and some current. So here's my magnets. They're kind of into some protective sleeve so I don't break them, but I'll have a magnetic field, and I'm not sure whether it's left or right, and in the short time I won't worry about whether it is left or right. Let me take a power supply and a couple of wires here, and I'll hook up what I affectionately call the Flintstone motor, because it works really on very basic, simple principles, and it supplies a torque. And so if I turn this on, yay, I get my Flintstone motor. And if we had more time, we could probably analyze which way it's going. But your author, as I said, does a good job, even though it's a long-winded. And he says, remember torque? Remember way back in Physics 110? Remember how do you do torque? And so he goes through and he derives a nice little equation. He gives you the picture, he gives you the torque, and he comes up with an important equation. So let me give you the result of this equation. And he says, how much torque do you get? So I'll put that over here. And so torque from my motor would be I for current, and I better talk about A for area, B for magnetic field, and sine for the angle, and there's even an N. And so the one that I need to mention right away is the area. And I'm going to ask you guys to go through the derivation because I think it'll make more sense. But the area is the area of the loop here. If I hold this up right here, you would say this is the area of the loop. Which it kind of makes sense because you would have this factor because this would be the amount of force. But then you would have this factor because that's the torque from the lever arm. And so between this factor and this factor, you end up with the area of the rectangle. N is just how many loops do you make. This little model here shows 1 loop. This one we wrapped around a lot. I forget how many times we did it. I think we did 200 times, and we just kept wrapping and wrapping and wrapping and wrapping. And so I would call this then the number of loops. How many times? And so then we can get a very practical device out of our magnetism, and that's an electric motor. I'm sure you're very familiar with electric motors and how useful they are, and how practical they are, and how common they are. And so this, again, I'll make it in my notes here, but I wrote down this would be a good time to do example number 43. And so I'll just say that on video and get a supplement of those out later today. But this problem has to do with motors and torques, and it'll have you calculate how much torque do you get from a particular motor. And then, of course, that brings us back. Well, that gets us to the last section. And section 9 here. Well, I'm going to I guess there's a 10. So 9 and 10 kind of go together. 9 and 10 is both good and bad in the sense of the work here, because a couple of very famous scientists, one is Ampere, the other two is Biot and Savart. They both took the next step, and when I say next step, did you notice that everything I've done so far says what is the force when it is in a magnetic field? Even though we started this chapter by me saying that a magnetic field comes from moving charges. But until right now, we never had a formula or a way to say how much is the magnetic field. So Biot and Savart figured out how to calculate how much force, or excuse me, how much is the magnetic field. So for example, they said, what if you just had a straight wire? How much would the field get you? Well, here's the good news and the bad news for us. Maybe it's more good news than bad news. Is in order to do their calculations, you need what is called calculus 3, vector calculus. It's, of course, beyond the requirements of this class. It's more designed for the engineers. So your author does this. Your author says, why don't I just give you the formula of how to calculate the strength of the field without proving it to you. So your author says, for a straight wire, the amount of the magnetic field would be this formula, where the R is the distance from the wire, the I is the current, and this new factor hopefully looks a little bit, remember the epsilon naught we had a few chapters ago for the permittivity of the free space? This is then the magnetic equivalent of that. So we call this the permeability of free space. So how does the magnetic field permeate free space? And so we have both a permeability of free space and the permittivity of free space, and easily confuse those. But the permeability is for magnetism stuff. What you'll need to know here is how to calculate this, and you need a number, and it's 4 pi times 10 to the minus 7. And if you study it, you'll kind of look at the units here. It's got to come out in Tesla here, but it's got a meter downstairs, and it's got an amp in here. So in the short time we have left here, I want to just come over here and say, let me introduce you to right-hand rule number 2 and this formula. Right-hand rule number 2 and this formula is simply saying this. If you have a wire that has current in it, so that's what this is trying to say, there would be a magnetic field perpendicular to the current. Remember the 3 dimensions I keep talking about? It's hard to visualize these things. So I'm going to hold this out here. What would be perpendicular to this line of current? A plane. And so the magnetic field has to be the same value, equally distance, so the magnetic field would be these circles around it. And so that's this visual picture. And an easy way then to figure out the direction of the magnetic field is to take your right hand. Here it is again. Right hand rule number 2. And just kind of pretend you're grabbing the wire. but you grab it so your thumb is in the direction of the current. And when you do that, your fingers will curl around in the same direction as the magnetic field. So not this, but this. And so if we're ever doing a problem and you need to know the magnetic field, and they don't tell you what the magnetic field is, but they do tell you you have a straight wire, you now know how to calculate the field. And you know how to get its direction by rule number 2. In fact, your author does this same procedure for a few other geometric shapes. He says this is the formula for a long straight wire. What if instead you have a loop of wire? Or what if you have a solenoid, which is really a bunch of loops put together? Well, let me show you these, and I'll put the formula on here first. For a loop of wire, this would be the magnetic field at its center. And in fact, if I hold up a loop, maybe that will help you understand what I'm talking about, something like this. And so if we wanted to know the magnetic field right here at the center, I would use that formula. But how do I get its direction? Well, remember, right-hand rule number 2 can be very useful. So if the current's going around this way, you can kind of imagine grabbing this part of the wire. See how my fingers go up on the inside? And then over here, see how my fingers go up on the inside? And then over here, see how my fingers go up on the inside? And so if the current was going around this way, the field would be upward. If the current had been going the other way, I'll take right-hand rule number 2, right? And I'll say, well, grab the wire there. See how my fingers go down? Grab the wire right here. See how my fingers go down? Grab the wire right here. See how my fingers go down? And so every little piece of this wire would be going down. And so again, if I wanted to get its magnitude, I would use that formula. If I want to get its direction, I would use right-hand rule number 2. And again, your author does a good job here of showing you a picture of a wire in a loop. See? And so there's somebody's right hand. There's the thumb in the direction of the current. There's the fingers going up. Fingers going up. And so everywhere around this loop it goes up. And so the field would look something like this. And that formula gives us a way to calculate it, but only at the center. But that's enough for us. We're not going to try to get off center. It gets way, way too complicated. Even this, we cheated you by just saying, what is its value? Now, what about the last one, the solenoid? Well, the solenoid is this little formula. It's the permeability of free space. It's the number of turns in the solenoid divided by the length of the solenoid times the current. And so right here is the number of loops. It's the same thing we did when I mentioned right here the torque on a motor. This is the length of the solenoid. And the other two I hope are obvious. This is the currents in the solenoid, and then this is the permeability of free space. So this really is what? And that's a fancy word, a solenoid. What is a solenoid? Well, you heard me say it at the beginning of the lecture. This is a solenoid. And so a solenoid really is just a bunch of rings, a bunch of loops. And so if you add this one and this one and this one and this one and this one together. So in this case, it says right on here that there's 180 turns. And so if I wanted to know how strong is the magnetic field inside of this solenoid, and so that's the other thing I want to put on here. This is the inside of the solenoid. This is the formula I would use. I would put right here 180 loops, and I would measure this length, which is 10 centimeters, and I'd put that right here. And then I'd hook it to my power supply. Maybe I'd hook it to a half an amp, and so then I'd put in half an amp. And then I'd multiply by the permeability of free space, and that would tell me the magnetic field inside this solenoid. And again, I would use right-hand rule number 2 to figure out its direction. And so this is what your author is trying to say here, that, hey, we would have this field, because they got the currents going up on this end. See, the positive comes out and the current goes around, and I'd put my right hand right here with my thumb going up, and my fingers would be pointing through the center of the solenoid. So that's what this is trying to say, that the field would go this way, right? And so here's the field. And then it would arc around on the outside. But on the inside is what I'm focusing on. The inside is what that equation is for. All right, well, we're out of time. We got to leave and go to lab and let the other class come in. And actually, we other than not getting a chance to do a few examples, we actually did cover this whole chapter. I didn't think we would. Hopefully it wasn't too much in such a short time, but also hopefully the next 5 days will give you plenty of time to start digesting that and letting it sink in and make more sense before the test hits us. All right, we'll see you guys next time.